All right, so I thought I'd give a brief proof of Dini's theorem from real analysis with all the details, all the nasty details. But it's a good exercise. So Dini's theorem, let X be compact. And then a bunch of conditions. We have a sequence of functions fn. Each fn is continuous on X. The fn's converge to some function f pointwise on X. That limit function f is also continuous on X. And the cardinal condition of the theorem, the sequence fn is monotone increasing on X. So let's just try to draw a little bit of what that all means, since that will be useful. So let's say I have my domain big X, okay? The fn's are continuous and monotone increasing. So they keep getting higher. Maybe this is f1, f2 must be strictly bigger, it never dips below f1. f3, f4, it keeps going up, but it will converge pointwise to f. That means there is some ceiling. There is some limit function f, which is the biggest, and they're all going to get closer and closer to f. And we know f is continuous on X itself, and closer and closer. Given all these conditions and the compactness of X, then we know fn converges to f uniformly on X. This is a theorem that gives you that the convergence is uniform given too many conditions. All right, we'll need one lemma for this, if you can even call it a lemma. This is topological continuity. So recall that if I have a function g from x to r, and g is continuous on X, that it is equivalent to say that the pre-image under g of every open set is open. Okay? So say in your head over and over, if g is continuous on X, then the pre-image of every open set is open. All right, so let's go prove this theorem. Because it is a proof of uniform convergence, we always begin with our beloved let epsilon bigger than 0. And now what? What we're going to do is we're going to take this problem of fn's getting closer to f and rephrase it a little bit. We're going to define a new sequence of functions g sub n equals. Notice that because f is the ceiling, f is going to be bigger than all of the fn's. So if I define the difference, f minus fn, the first thing I know is this thing must be bigger or equal to 0. The ceiling f is always bigger than the fn's. But furthermore, since fn converges to f pointwise, these fn's are going to get arbitrarily close to f. So in fact, we even know more. We know that the gn's themselves are going to converge to 0. This won't be needed really much in the proof. The important thing is the f minus fn's, bigger than 0. And the last thing, note that because we prescribed fn and f to both be continuous on X, then their difference, gn, is also continuous on X. Gn is continuous on X, each gn. So really, all I've done is, take the fn's that are increasing to f and rephrased it as a bunch of functions gn that are getting closer and closer to 0. Maybe that's g1, maybe that's g2, that's g3. They're getting closer and closer, and they're going to converge down to the 0 function, since fn is converging to f pointwise. Smaller and smaller. So what are we going to do with this? Well, define, now this is the fun part, the tricky part. The set E sub n, I'm going to define this to be the pre-image of G sub n of the interval negative infinity to epsilon. Now, what a mess that is. Let's go draw some of these ENs to see what this is looking like. This is sort of the meat of it. Okay. I'm going to draw a big coordinate plane. Here we go. Yes. Maybe we're going to let this whole domain here be capital X. So what's going on here? Well, we had an arbitrary epsilon bigger than 0 prescribed. Let's say that that height is over here. So that I just drew, that dotted line is the height of epsilon bigger than 0. Epsilon, really. we know the GNs are getting lower and lower. Maybe here's G1. Here I go. Maybe that's G1. G2 must be lower, so maybe G2 is a little lower like this. Maybe G3 is even lower than that. So let's go see what these pre-images are going to look like. This set is the set of all inputs. Remember, pre-image are inputs. It's the set of inputs that G sub n will send to minus infinity epsilon, which is just essentially less than epsilon. So let's just do it for G1. Okay. So if I look at the graph here, E1, think as the set of x's such that G1 of x is contained in minus infinity to epsilon. This is the definition of pre-image, but that's just saying G1 of x is, well, less than epsilon. Apologies if the camera was too low. E1 is the set of all inputs x such that G1 of x is in here, that is less than epsilon. Okay, well, if we go down here to our picture, here's G1, the top blue line is going down. It's still above epsilon here. Oh, at this point right here, G1 dips below epsilon. And it stays below epsilon until this point. Then it goes above epsilon again, and here it goes below epsilon again, here it goes above epsilon. So these two squiggles on the x-axis here, these are the inputs such that G1 of those inputs are less than epsilon. So these two squiggly intervals here is E1. Okay. E1 is that these inputs union these inputs. How about E2? Well, I don't have to write the whole thing again. It's the set of all inputs that G2 of x is less than epsilon. We can track the graph of G2. Here's G2, it's coming down, down. Okay, as early as here, that x, G2 is dipped below epsilon. It's going to stay below epsilon for quite a long time. Dips back up there, dips back down here, and dips back up here. So, what is this saying? Maybe I'll use spirals this time. The union of these two spirals sets, that's E2. And notice something that is no coincidence. E1 is contained in E2. Right? The minute I went to a lower down Gn, from G1 to G2, well, because G2 is lower than G1, it's sort of like it has to have it has to have all the inputs that come up to epsilon by G1 too. It's just further lower down. I'm going to capture more values. And if you do this for G3, G4, which I encourage you to do until you see what's going on, hopefully you'll see that the ENs are nested. I guess we can quickly do G3 once more so you can see how quickly it's going to encompass the x-axis here. But G3 dips below epsilon as early as this point here. And it's essentially entirely below. This little dip here, this whole thing. Maybe use triangles this time. All of this input values are mapped below epsilon by G3. So all of those triangles all union together is E3. And this is sort of the intuition to have about this theorem. Right there. So now it's time to go back to the land of rigor and prove everything rigorously, because that's how we roll here. Claim. A claim supported by picture. The ENs are nested. That is, En is contained in En plus 1. And the picture tells us the reason is because the GNs are decreasing. So that's going to be the key to the proof. This is just a set inclusion proof. Let X be in En. En is just the pre-image of this. So that implies G sub n of X is going to be in this interval that is less than epsilon. Okay? But because the GNs are decreasing, then certainly Gn plus 1 of X is less than or equal to Gn of X. That's what it means to be decreasing. Gn of X was less than epsilon. So Gn plus 1 of X overall is less than epsilon. And that, by definition of pre-image, means X is in the pre-image of negative infinity epsilon under Gn plus 1, which is precisely En plus 1. Simple as that. The ENs are nested. But they are not just nested. There's another thing that we can say about them. Recall that, remember, since F and Fn were both forced to be continuous, the Gn is continuous on X. Gn is continuous on X. But then, negative infinity to epsilon, that's an open set. Negative infinity epsilon is open. So by topological continuity, its pre-image must also be open. But its pre-image is precisely En. So its pre-image En is also open. Oops, I've been cutting you guys off. Yes. So recall G is continuous on X because F and Fn were both forced continuous, but everything less than epsilon strictly, that's an open set. So because of the continuity of G, by topological continuity, the pre-image of this En is open. So now, what we essentially have is this chain, E1, which is, yes. So E1 is going to be contained in E2, contained all the way up. And this goes on, goes on and on. And each of these are open. Well, wouldn't it be nice if all of these ENs were an open cover of X? That's how we know we're halfway done. And the picture should tell you that this ought to be the case. Because look down here. We have these, E1 is the little squiggly, E2 is a spiral, E3 is a triangle. It's just getting bigger and bigger, and you can sort of intuit eventually it's going to encompass all of the domain big X. Because the GNs are decreasing towards 0. You're not going to leave any room eventually for things to be not less than epsilon, for arbitrary epsilon. But that's all words, let's prove it. Claim. The union of all the ENs is an open cover of X, or for X. Well, the open part is done because we have shown that they're all open by topological continuity. It remains to show that they cover X. A quick proof, really. Let arbitrary little x be in big X. Here is what we're going to really use the pointwise convergence of Fn to F. The fact that Fn goes to F pointwise, okay, then the sequence F sub n of X will converge to F of X. This is a sequence convergence here. So I'm fixing the X, and I'm just taking F1 of X, F2, F3 of X. We know it converges pointwise to some F of X. Okay, then, because of that, for the epsilon that was prescribed at the very beginning of this proof, for epsilon above, we know there's going to exist some big N and N, such that for all n bigger than big N, we have f of x minus fn of x is less than epsilon. There's absolute values, of course, but remember, f is a ceiling. F is always bigger. So I can just write it like this. but f minus fn is precisely gn of x less than epsilon, which means x is in the pre-image of everything below epsilon, which is en, which is part of the open cover of all the ens. And that concludes that. So we have now proved that all of these ens is an open cover for x. But remember, they're nested, right? Okay. Each one contains all the previous ones. So, in a way, and you'll see why this matters, because now we're going to use the compactness of x to extract the finite subcover. So let's go do that. Since x is compact, there exists a finite subcover of the union of all of the ens. So maybe it's just, just as an example, maybe the subcover is, E and 1, union E and 2, union, but it's only finitely many, right? Maybe E capital big N, and let's just have this E sub big N be the largest of all of the others in the finite subcover. Because remember, they're all nested. So if I take a finite many of the ENs, one of them, the biggest one, is going to contain all of them. So let's let that biggest one be E sub capital N, okay? So then letting En be the biggest, that finite subcover really is just subsumed inside E sub big N. So what does that mean, this finite subcover? Well, that actually finishes the proof, because this finite subcover, which is just the biggest one, so E sub capital N, covers x. That is, x is contained in E sub big N, this singular E sub big N. Now let's really decide what this means. This inclusion means that for all x in big X, x is contained in G sub big N, the pre-image of G sub big N of minus infinity to epsilon. That is, G sub big N of x is less than epsilon. But let's have an arbitrary little n be bigger than big N, because we have to do that for the uniform convergence. Recalling that the GNs are decreasing, that means G sub little n of x will be less than or equal to G sub big N of x, which is less than epsilon for all n bigger than big N, right? GNs were decreasing to 0. So if n is bigger than n, then they gotta be smaller than G sub big N. But what is G sub what is G sub little n of x? That's just f of x minus fn of x. F is the ceiling. I can put absolute value if I wanted to. F sub x, absolute value is less than epsilon. Oh, there we go. Uniform convergence proved. And that is the proof of Dini's theorem. So just to sort of go through all the requirements of the theorem, they really all do play their piece. We needed the continuity of f and fn to guarantee that gn was continuous. So I could use topological continuity to get that each en was open. So I could have the open cover. That's why we needed continuity. And we, of course, all the monotoneness lets all this happen. The thing that might be a little subtle is, where was compactness used? Why do we need compactness? Because if we look at this picture down here, well, it didn't look like I needed the closedness and boundedness of this domain big X. The drawing didn't seem to show it. Now I'm going to show you why compactness is necessary. Suppose that we were over the open interval, open at 0, maybe it can be closed at 1. So let's say X is the half open Open at 0, closed at 1. Okay? Let's say that my GNs were such that they asymptotically go to infinity as they approach 0. So maybe here's G1, here's G2, here's G3, and you know, these functions are still going to converge pointwise to the 0 function. So what goes wrong? Well, remember, all of that proof worked because I had a finite subcover. So I could extract a single capital E sub capital N that contained the entire domain. And that let the rest of the proof be finished. But what happens close to 0? Well, if I take x values that are closer and closer to 0, well, I'm going to keep on needing to go to higher and higher up g's to get it below epsilon. All right? If this here is epsilon, maybe for this x here, the one that you can barely see, maybe it'll finally come to be below epsilon on, you know, G4 or something. But if I take x's closer and closer, I have to keep going more and more. I have to keep going to the next g and the next g and the next gn to get that below epsilon. And that prevents there being a finite subcover. It will still cover. All the ENs will still cover x, but there won't be a finite number of them, because when you have this asymptotic thing, you always have to go to more later down GNs to get arbitrarily small values of x below epsilon. If you draw the picture, and hopefully you'll see that. So that is Dini's theorem. The last thing of note is the proof also holds if the monotone decreasing. Virtually the entire argument stays the same, just instead of f minus fn being g, it's fn minus f is g. And then a few other changes, but they're minor.